Today we're going to talk about how to get oil and gas out of the ground. Well, the simplest way is to let it come to us. This is an artesian well. Remember from your vocabulary that artesian means that it's a liquid under pressure underground. This is Spindletop, Texas, that started the Texas oil boom. That gusher ran for 9 days at a rate of about 100,000 barrels of oil a day before they were able to cap it and start holding on to that oil. So if you can find an oil reserve that's under pressure and it comes out by itself, that's certainly the easiest way to get it out of the ground. If it won't flow on its own, then it can be pumped out. And if you live in Texas, of course, you've seen pump jacks. They're all over the place. This works very much like suction on a straw. You drill a hole straight down into the layer that contains oil or gas and start sucking it out. That works for a long time, but eventually you get to the point where the oil that's in the rock is really clinging to the rock and it's tougher to move. And so in that case, we can move to a secondary recovery method, which involves an injection well. And in this case, a CO2 injection well, where you drill a well nearby, inject carbon dioxide, and that comes out tiny holes into the layer where the oil is, and then pushes the layer off of the rock it's clinging to and towards the well that you're pumping it from. So this additional recovery of oil is a way to get a lot more of the oil that remains in the rock. Now, of course, we do a fair amount of drilling in the U.S. Offshore, and this is an example of the offshore oil rigs, some sketches of what they look like. Many of the offshore oil rigs in shallow water, and most of them are in shallow water, are simply attached directly to the ocean floor and drilled from there. But there's been more drilling lately in the deep Gulf of Mexico, and these rigs are floating rigs, and they're attached by cables anchored in place, but that long black drill in the middle is essentially unprotected other than the cables holding it in place as it goes all the way down through the water and then into the ground. Now, the really positive thing about deep water drilling is that under all that water and then deep under the surface, that oil tends to be under pretty high pressure and it flows fairly easily, as you saw in the Deepwater Horizon accident a couple of summers ago. But it's really expensive to put one of these rigs in place. The latest one that Chevron is working on out in the deep water is going to cost $8 billion. That's billion with a B. So you can see that there must be a great deal of oil down there to recover if it's worth investing that much money to get it out of the ground. So over the years, this is what happens in an oil field. First, the oil field empties pretty easily, and then you reach a point where the flow starts to slow down, and you can involve a secondary measure of recovery at that point. But eventually you get to the point where the well dries up and eases to a trickle. It doesn't mean all the oil is gone. It just means that it's difficult to get at the rest of what is there. We define that concept as peak oil. And what that means is it's the time when that oil well or that region where you're pumping reaches its maximum. And generally, when it's at its peak, about half of the oil has been produced. And there's still another half to get out. You might not get all the other half out, but there's still some there. So peak oil does not mean running out of oil, but it does suggest that the rest of the oil is going to be harder and more expensive to get at. So what happens after you pull the oil out of the ground? Well, the next thing you have to do is separate it at a place we call a refinery into the different kinds of petroleum products that you might want to use. And this is done very much like the separation by mass of oxygen isotopes, for example. Different kinds of hydrocarbons have different lengths of hydrocarbon chains, the CH chains that make them hydrocarbons. The shorter ones, gasoline, tend to be much lighter weight. Longer they are, kerosene, diesel oil, fuel oil, have longer carbon hydrogen chains and are therefore heavier. And because of this difference in mass, they can be separated by temperature. And so that's what a refinery does. It takes crude oil in, it heats it to different temperatures at different levels in the refinery, and then those different hydrocarbons are pulled out for the various uses that we have for them. So how much oil do we have? Well, the first oil well was built in Pennsylvania in 1859, and at that time it's estimated there were about 2 trillion barrels of recoverable oil somewhere in the ground all around the world, unevenly distributed. By 2006, we'd used up nearly a trillion, so about half of the natural oil that has been produced has been already taken out of the ground. That means the other half is still there, but that's not a whole lot. In 1856, a guy named M. King Hubbert, he's a petroleum geologist, he worked for Shell Oil, and he was going to give a talk to a bunch of petroleum geologists in San Antonio, Texas, in which he predicted, based on his understanding of oil extraction, that the lower 48 states, the U.S., would peak in oil production in 1970. Up until just before he gave his talk, his bosses at Shell were begging him not to, but they needn't have bothered. No one believed him. In fact, they laughed him off the stage. However, this is what U.S. oil production actually looks like from 1859 to 2004. In 1970, in fact, we did peak, and production started to decline. It bumped up again in the early 80s, and that is the discovery of ways to get oil out of Alaska. And of course, that's dropped off again too. So Hubbert was right to an extent. But the story isn't over there. Look where we are today. In 2007 or 8, it started to tick back up again, and it's been on a very steep increase since 2010. What accounts for this increase in oil and gas productivity in the United States in the last half a decade? New technologies. There were 2 new technological innovations that made it possible to get oil and gas out of very tight rocks called shales. And we have always known that there was oil and gas in these rocks. We just didn't have any way of extracting it before because, as you recall from your sedimentary rocks, shale is a very fine-grained rock with fine pores that aren't well connected. And so, although there's oil and gas in there, you can't just drop a straw in and suck it out. So the 2 technological innovations were, first of all, horizontal drilling, and that is drilling down to the gas layer and then drilling parallel to the layer for some distance, and sometimes that distance is up to a mile. And then the second innovation is called hydrofracturing, or fracking for short. So this hole is drilled horizontally, and all along the pipe in the horizontal part there are tiny little holes. And then once that's all in place, fluid is pushed down the hole at very high pressure so that it bursts out of those tiny holes and fractures the rock around it. Now that fluid has a little bit of chemicals in it that are sort of soapy, that help the fluid move easily into these little tiny cracks, and it has sand in it to hold the cracks open. And so those fractures open up and oil and gas flows from those fractures back into the well and is pumped out. So that's what hydrofracturing is, or fracking is. And that innovation has allowed the U.S. to recover oil and gas from places that weren't recoverable before. So geologists named this new kind of resource unconventional, so it was brand new. And this is a chart showing you some conventional resources, typical oil and gas traps where oil and gas has migrated up against a barrier like this shale layer that it can't get past, and you just drop a straw into it and suck it out. And then unconventional resources like oil and gas shale and these tight gas deposits that you have to fracture in order to loosen up and remove the hydrocarbons from the rock. That's really changed the picture of oil and gas recovery in the United States and led us to the brink of potential of being independent of foreign imports if these if these resources are developed. In Texas, we have the long-standing Permian Basin out near Odessa that has a lot of conventional oil and gas, and now a fair amount of shale gas as well. In the Barnett area in Dallas-Fort Worth, and then the Eagle Ford Shale, which is southwest of San Antonio. Um, all of these places have gas in the shale, and Permian Basin and Eagle Ford have oil and gas in the shale. So does the Bakken up in North Dakota. I'm sure you've heard about that, if from nothing else than from the television show Blood and Oil. And then another very large play is out in Pennsylvania, the Marcellus Shale. That is mostly gas only, not liquid. And therefore, right now, there's not a lot of drilling going on in the Marcellus. The U.S. today doesn't have a very good system for using the natural gas that we can produce. If we had more power companies using natural gas to make electricity and more transportation using natural gas, then the price would go up and the ability to recover it would increase, or the economics of recovering it would move to the side of drilling more in places where natural gas is so abundant.